Welcome. In this session, we will look at an example where we find a function from one of its higher order derivatives. We will again do an initial value problem so that at each step we get a single answer. Basically, undo the derivatives one by one. So if you are given the second derivative, you will do two antiderivative. The first antiderivative gives you the first derivative, the second antiderivative gives the original function. If you are given the third derivative, you will have to do three antiderivatives. So go from third derivative to second, then to the first, then the original function, so on. In most applications, again, we don't really see more than the second derivative. Example is, we will do a problem where we are given the second derivative. So the problem is g double prime equals 6x plus 5 over x squared, g prime of 1 equals 2, and g of 1 equals 3. To determine the function uniquely, we need the value of both the first derivative and the original function at some number. We'll do one antiderivative that will give us g prime. Since g double prime is the derivative of g prime is an antiderivative of g double prime. To find the antiderivative of 6x plus 5 over x squared, I'm going to write it using negative exponents as 6x plus 5x power negative 2. Now I can apply the power rule to each term. An antiderivative for 6x is 6 times x squared over 2, it's 3x squared. And for 5x power negative 2, it will be 5 times x power negative 1 over negative 1. And of course, we have to have the constant of integration. I will write it as C1 because we'll have a different constant in the next portion. So to avoid any confusion, use different names. So we get 3x squared minus 5x power negative 1 plus the constant of integration. Since I have to do some calculations, I will write this in terms of fractions. When x is 1, g prime is 2. So if you plug in 1 for x in this expression, I should get 2. That gives me an equation for C1. I'm going to solve that for C1. So on the left, I have 3 minus 5 plus C1 equals 2, or negative 2 plus C1 equals 2. So C1 is 2 plus 2 or 4. Now I put this value of C1 in this expression. That gives me g prime. So g prime is 3x squared minus 5 over x plus 4. And I have to do its antiderivative to find, because what we have is only g prime. An antiderivative for 3x squared will be 3x cubed over 3, or x cubed. For minus 5 over x, I can think of it as negative 5 times 1 over x. An antiderivative for 1 over x is basically ln of absolute value of x. For 4, an antiderivative is 4x. And then I have a constant of integration, possibly different from last time. To find this constant of integration, I am going to use the remaining piece of information, g of 1 equals 3. In other words, if I plug in 1 for x in this expression, I should get 3. So 1 cubed minus 5 ln 1 plus 4 times 1 plus C2 equals 3. ln 1 is 0. So the left-hand side simplifies to 1 minus 0 plus 4. That's 5 plus C2 equals 3. So C2 is 3 minus 5, or negative 2. And I put this value of C2 in here. That is the original function. Now, there is one thing I should point out. While talking about antiderivatives, I said that antiderivatives are unique up to a constant. That is not quite right. If you take two antiderivatives of the same function in the same interval, then the difference will be a constant. But if you take antiderivatives in disjoint intervals, they might be quite different. Or they might differ by different constants in different intervals. So most of the time it's not a problem, but if you have a function whose domain is not a single interval, you need to be more careful. In this case, we have the term 5 over x squared. So the domain of g double prime consists of non-zero number, which is two intervals, negative infinity to 0 and 0 to infinity. Since the initial value is given at 1, which is in the interval from 0 to infinity, strictly speaking, we can determine g only in that interval. That's why in the problem it says find g of x for x greater than 0. And since x is positive, we didn't really need the absolute value. That's why in the answer I left out the absolute value. This concludes our discussion of initial value problems for now.